All right. Okay, so today we are going to take what we did last time on Tuesday and apply it to a problem similar to your homework problem and a little bit to your lab problem, kind of where we're going. So just some announcements here. The next ICA is due before lecture C1, which is next week. I think it's Tuesday. I think that's the next lecture. There, as a reminder, homework B1 is available on Canvas, an individual assignment. I say preferably typed. You know, that's not necessarily it's not necessary, but it definitely has to be legible and clear. You're gonna go an engineering job, you're gonna start using a lot of Microsoft Word, I have to write a lot of words. First time how much writing practice you there's sort of, so when I put you don't have more in the response. So a shot or they sorry that those online. I think my Zoom died there for a second. Hopefully you can still hear me. And if you can, put something in the chat just to make sure. And let me reshare this screen. Thanks for that. All right, I think we're back here. Good. So some clarifications. On question 1, I ask you for at least 2 examples of each category. If you're having trouble thinking of 2 examples, you might be thinking of too broad of a category. So you might have a system where an animal is your entity type. Well, you can think, well, there's actually multiple types of animals. Well, maybe dog, cat, bird, human, those are all 4 different types of animals, and each one of those themselves could be a different entity type. So if you're said, I can only think of, you know, if I'm thinking about a doctor's office where, you know, patient might be the entity. Well, there are multiple types of patients. There maybe are patients that arrive under emergency, and there's also patients that arrive by appointment. And you can imagine they have different arrival rates. So those 2 different types of patients could be 2 different types of entities. It's true that you could have one broad type of entity and differentiate them with attributes later, but a lot of times you just create 2 different types of entities. So if you're having trouble thinking about multiple types, think about ways you can break those types down, and that hopefully will give you the additional types. Other things, so in question 2, the state variables and cumulative statistics come from table 3.2 in the lecture textbook, the Banks book. So this is a quick primer, but you can find this in the Banks book. LQ is the number of customers currently waiting for service at this instant of time. LS is the number of customers currently in service at this time. So LS will always be either 0 or 1. LQ plus LS will add up to however many people are in the kind of line variable that you maintain in that problem. There's also a number of cumulative statistics in D, S, and F. In D is the number of customers who have departed the system, and I say by this time, but really we focus on it at the end of the simulation. That's what I mean by cumulative. It's sort of accumulating up to this point where our main goal will be to take it at the end of the simulation. S is the sum of the response times for all customers who've departed by this time. So again, it's accumulating over multiple times. And F is always going to be smaller than ND because it is the number of departed customers who have spent 5 minutes or more in the system. So if 5 people have left, but only one of them have spent 5 minutes or more while they were in the system, then ND will be 5 and F will be 1. So, and then just to clarify, the response time duration is the total time a customer spends in the system from arrival to departure. It is not just their service time. So we give you a list of service times. And so it might seem a little funny, like, why am I counting up the number of customers that have a service time greater than 5 if you just look at the list ahead of time without running the sim? That's not what response time is. Response time is the service time plus their delay in waiting to start service. So that's why we have to subtract their departure time or subtract the arrival time from the departure time to get their total time in the system. And that is what you're then checking against. If that number is greater than or equal to 5, then you increase this F number when they depart. Otherwise, you don't increase F, but you always increase ND. So those are some clarifications on that. Any questions on the definition of these variables that go in the top of your table for question 2? And I'll also check online if there are any questions. Okay. And I might also open up on this terminal, the meeting pulse questions as well. Okay. All right. Also in question 2, I get sometimes people ask, like, why is there an empty gap as the first inter-arrival time? That's not a mistake. The first customer doesn't have an inter-arrival time before her. And so that kind of empty space is meant to imply that the first customer has a service time associated with them, but they arrive the time the system starts. So the first inter-arrival time is really the time before the second customer. It's the time between the first customer and the second customer. That's the reason why there's kind of a gap there. So that gap is not a mistake. When you need another inter-arrival time as you're doing the simulation, you just take the next inter-arrival time and it'll just, whatever, you just go down the list. And so they're just spaced that way because the inter-arrival time, the first inter-arrival time is really sort of more tightly coupled to the second customer, which is why it shows up there. But you really think of those as 2 independent lists, the inter-arrival time list and the service time list. And then some sanity checks. So when you're doing question 2, filling out that table, the future event list will only ever have 1 arrival event at a time, and exactly 1. It will never have 0 arrivals. It'll never have 2 arrivals. If you've put 2 arrivals in your future event list, then you've kind of tried to think ahead and you've tried to anticipate all the other arrivals and put them in there. The computer won't do that. The computer, when it generates a future event list, will only think, all right, I'm done with 1 arrival. I need to schedule the next arrival, and then it stops. And it waits to do the processing of the next arrival after it processes the next arrival. So there's only ever exactly 1 arrival event in that future event list for this single channel queue. The future event list will have no more than 1 departure event at a time. So it might have no departures. So it might be that you don't know when service is going to end next because currently things are idle, and you're waiting for the next arrival. But if there is a customer in the system, you're going to have their departure in the system as well. And but that's the only departure you'll have there. So the FEL will have no more than 1 departure, but it might have no departures. The clock will always match the time in the first event record from the FEL in the previous line. So as you're going down, and we're going to do an example of this today, so you'll see that. But if you're doing your homework and your clock column, whatever that variable is in that row, if you look at the FEL from the previous row, the beginning of that FEL should match the clock there. That's another sanity check. If it doesn't, then something might be wrong. The sum of LS and LQ will always equal the number of customers in the line state variable, the checkout line. And then as I mentioned before, the LS, which is the number of customers currently being serviced, is either going to be 0 when the system is idle or 1 when the system is busy. And then the cumulative statistics, because they're cumulative, will always be non-decreasing. They'll never decrease. They might stay the same. F will always be less than ND, as I mentioned before. And response time jumps in S will always be larger than or equal to the corresponding service duration, because the response time for each customer is their service duration plus the amount of time they've waited before service starts. All right. And then if you do the bonus, then this sort of hint is you can use the bonus, which is sort of to do the same problem, but in this kind of Excel-based format. The answers you get to the bonus should be consistent with the answers you get up here. So the answers you get when you do the hand simulation, kind of the time by time, if you say, well, by time 15, I've had 3 customers, well, then you should be able to go into the Excel column and say, well, by time 15, did I have 3 customers? And so those 2 things should match. You should get the exact same results. All right, any questions about the homework clarifications or anything about the homework in general? Okay. And there's a lot of resources for both the homework and the lab that have been posted on Canvas. So I've got, I think, a bunch of sample problems that I've done for you for the homework, like a bunch of, that you can download. I think I've got a video of me doing, I think, both the homework and I think the lab too. And so the big difference between the homework and the lab hand simulation is in the homework, you get 1 arrival at a time, but the timing between arrivals is random. In the lab, you get the time between arrivals is fixed. It's always whatever, 1 minute, but the number of arrivals you get is random. But otherwise, the hand simulation runs very, very similar between the lab and the homework. All right, just a reminder, IISC Rockwell competition. Just like I introduced last time, there's also the FlexSim competition, which is more based on healthcare, and several other DES competitions like the Simio competition. So just as a reminder, those are out there. The FlexSim has an entry of like, it's like September 20th or something like that. So it's a little sooner, whereas the arena competition, the entry, I think is September 30th. Okay. Questions? Still. All right, so we are now firmly within discrete event system simulation, the very process-centric perspective. I'm just going to double check for questions online. Okay, and so when we talk about these discrete event system simulations and these processes, then we're thinking about like intersections like this as interacting processes. So these cars are on the road. There's people and bikes that are on the bike paths and the sidewalks, and all of those coexist and compete for common resources. So the resource that's always there is the road. So spaces on the road. So the crosswalk is a sort of a finer scale resource where a car that needs to go from north to south, that car has to cross across the crosswalk, but it can't do that while there's a pedestrian in the crosswalk. So you can imagine modeling this crosswalk as a resource that, while certain entities have access to it, prevent access to other entities. And that's kind of the fundamentals for discrete event system simulation, is we model the time in which entities take while they're monopolizing a resource. And so we could model with a stopwatch, what's the average time it takes for someone to cross a road? And whenever someone arrives to a crosswalk, if the crosswalk's empty, we know then that that distribution will then govern how long that crosswalk will be tied up handling that person, preventing a car from going across it. We could also model with a stopwatch on average, or what's the distribution of time it takes for a car to cross across that crosswalk. And while a car is crossing across that crosswalk, a pedestrian won't be able to use it. So those interacting processes come together over the common resources that they compete for. And those are the types of models that we're building here. So that's all I'm sort of saying down here. So that's all of the models that you build. The resources that you identify are the things that are under competition. And those are kind of the fundamentals to this. The entities just kind of come and go. So a common, choosing the right entities. So if we think about this is our general model here, where we've got entities that arrive, they have to wait for a particular resource. Then we can think about different systems that kind of have this structure, and we can figure out what are the entities and what are the resources. So in each of these systems, the resources will be the things actually doing the valuable work. Sometimes we call this value added time. So this is something that You can't get around it. You have to spend this amount of time doing the work. But then you've got the waiting time, those delays, and that's the non-value added time. That's time that just comes from the fact that entities don't kind of line up in a convenient timing, and so they have to wait for other entities to get out of the resource. So entities wait for resources, and resources are always there performing activities, although sometimes they're idle. So as an example, if we think about a shipping system, depending on the question we're asking, then different things can be the resources and different things can be the entities. So it has to really be driven by the research question. I say that, but I mentioned the doctor's office earlier. There are, when you're in your homework assignments, when we ask you, what are some example entities? Try to think of the most conventional case. So if you are saying that I'm modeling a doctor's office, you might imagine some weird corner case where doctors are entities, like somehow a doctor, I don't know how a doctor would arrive at the doctor's office and be an entity. But to me, a doctor's office, I mean, the name's in there, doctor. It's like, it's the place where the doctor lives. The doctor is the resource in a doctor's office. The patients are the entities. So if I ask you for entities in a doctor's office, I'm not looking for patients and doctors. It would be hard for me to easily imagine a model. I'm not saying the one's not out there, but if you want to make it easy on the grader for your homework assignments and things like that, try to think of kind of the most natural way to model these systems. And in things like doctor's office, I'm going to try to give you examples where there is sort of a natural way to think about what the resources are. And in a doctor's office, the thing that is always there are the doctor, the nurse, the waiting room. These are all resources in a doctor's office. The things that need access to those things, but will arrive randomly and leave and then be gone forever, those are the entities. So patients are the entities, different types of patients are the entities. Maybe people dropping off deliveries are the entities. So there are different things that arrive and leave a doctor's office, but the thing that's always there, that's the resource. But in theory, for more complex systems, it's going to vary by the question we ask. And so an example of that is I could ask a question, on average, how long does each container take to reach its destination? This is a very valid operational question. Somebody might say, I want to know about the performance of our system. How long are we delaying, or how long is each container taking to reach its destination? So if I were to ask this question, then I'd say, well, then what are the entities and what are the resources and all that? And then sort of like, what is sort of a choice for the entities? So in the shipping system, if I'm asking how long does each container take to reach its destination, when I ask what are the entities, what I'm really asking are what things are being delayed. Like here I'm saying, like, I want to measure something that's being delayed, and the thing that's being delayed is the entity. So what's being delayed here? What are the entities that are relevant to this question? Anybody? Containers, right. So the containers are the entities, because those are the things that we're doing our statistics over the containers. We imagine a random container arrives to this shipping system, and it has to get somewhere. And the time it takes to get somewhere, that's going to be depending on how well we do our operations. And so that timing there, because that's being averaged over a potentially infinite number of entities, the entities are the containers. And then the resources are the things that the entities are waiting on. So a container shows up at a port, it can't go anywhere unless there's a ship available for it to be loaded on. So the ships are the things that are causing the delays to the containers. So in this case, the ships are the resources, and maybe the things that are involved in loading onto the ships. So maybe the cranes that move the containers from the dock onto the ship. Maybe those are also resources that could be tied up. But all of that detail, of all the microscopic detail of the cranes loading and all that, can be abstracted away into a general activity of loading and unloading. So you can imagine a ship as a resource. Is a ship available? Great. The ship is the server. It's the resource. It's available. How long does it take to do the process of loading the container onto the ship? Well, at the microscopic level, there's all of these different things that happen, but we just use a stopwatch and we go over and we measure for containers, we get a distribution of times. So for some containers, it took a half hour to load it onto the ship. For other containers, it took 5 minutes. And we get a distribution of that. And that tells us, without having to model all the microscopic details, the duration of the loading activity. And then how long does it take for most ships to reach their destination? We can look in a data table somewhere and see the average shipping route takes this long. But some take longer, some take shorter. So we got a distribution of times, we can draw that, and it abstracts away all the details of the shipping routes. And then they reach their destination, and then they get unloaded, and we can use a stopwatch, and we can measure what's the distribution of times it takes to be unloaded. So all those 3 distributions, those go into 3 different process blocks inside Arena, and they abstract away all these microscopic details and just get replaced by 3 different activities. But in order to even start any of those processes, you might have to wait because the ship might not even be available. So the ships are the resources whose availability causes entities to wait. So are there any questions about this example? So for this question, entities are the containers, resources of the ships, and the activities are all the things that get the entities onto the ships and get the entities to where they're going and get the entities off the ships. That makes sense so far? All right, I'll check online too. Nothing in the chat. Okay. All right, so I can ask a different question. What is the longest duration a ship will stay at one port while unloading and loading? So now I'm not interested in the ship, or I'm not interested in a container over its lifetime from dock to dock. I'm interested in a ship and how long it takes to actually get its unloading and loading done. And so now I'm actually modeling some of those more microscopic processes here. So because I'm focused on the ships and maybe the containers are my entities here. So now I actually am not viewing the ships as a resource. I'm modeling the ships as something that arrives to a port and then is stuck at the port during the unloading process and then departs the port. So for this research question, then the ports are the resources and the ships are the entities. And the loading of each container is an activity performed by the port. But the point here is that because my focus is on a slightly different question, than something that was previously viewed as a resource is now viewed as an entity, because my operational focus is on activities that are more focal to ships than they were to containers. So there happen to be containers on ships, and maybe I need for convenience to still model those containers, because a ship with 5 containers, it might be different than a ship with 100 containers. So in the muffin baking simulation you do in lab 2, you can think of the containers as the muffins, for example. And so some ships have got different batches of muffins. So I might still need to keep track of the containers, but the real focus is how long on average for the whole batch, for the whole ship it takes to load and unload at a particular port. And so on. So that's another way I can think of this. I could do another question. Will opening a new canal increase the total number of ships loading at ports per day? So here, what's a resource for this question? Instead of asking about an entity, I'll ask what a resource is. So for this research question, what do I definitely need as a resource in my model? What is the major thing, the major bottleneck that is going to delay my entities? Yeah. So the routes are important, but I don't view necessarily that. I could view the routes as a resource, because I could say that there's only 5 routes and you got to get on one of them, and whenever one route is saturated, then you got to wait to get on that route. So that could be one way to go. What's another thing that I might have to consider here? What's something that this question suggests will be majorly limiting in getting a ship from, say, one side of the continent to another? Yeah, a canal. So the question mentions, well, this is effectively, will increasing my resource capacity, how will that change the performance? This is a lot like, will adding another cashier improve the grocery store operations? Well, the cashier is the resource. here, this is implying that resources, that the canal is the resource that everyone's waiting on. So I might say that my ships are the entities and the ports and canals are the resources. And the canal operation, so operating the locks, etc., those are the different activities that occur that will delay things from getting through these canals. And so if I only have one canal, I run my simulation, I'd say, well, if I think my canal is the critical bottleneck, then hypothetically speaking, if I were to add a second canal, I should get a major increase in performance. So I go and I simulate adding a second canal. Now, my hypothesis could be rejected. It might be that when I add that second canal, it doesn't make a difference. Then the null hypothesis might be that it doesn't make a difference, and that could be rejected. And that if I add the second canal, then I find out that I get a huge increase in performance. And so we don't know where the bottleneck is, but if we, hypothetically speaking, want to say maybe the canal is the major bottleneck, well, then I should be able to add another canal and see a change in performance. And if I do or don't, that informs whether I should recommend investing in the huge cost of adding another canal. So the canal is the resource here, or maybe represents like maybe canals are the general resource, and we're talking about the resource capacity, whether there should be one or two, as an example. Okay, so questions about that example, does that make sense? Online, any questions? Great. Okay. There we go. All right, so I mentioned entities move in the model. They're often sort of like cars coming into car washes, people coming into banks, into grocery stores. Often they're moving in the real system, but they don't have to be. So in general, the big process here is that an entity arrives and leaves, and there are different ways that could happen. And so I talked about a vacuum cleaner. That is a resource. There's only one vacuum cleaner doing the whole job of cleaning the floor. But if we're modeling an autonomous vacuum cleaner and the operational policies on, if it detects a particular type of dirt, should it linger in an area or should it go and find another area? And so these vacuum cleaners have the ability to do that. They can decide how long to linger in different areas. And so we might want to model the operational policies on these vacuum cleaners. If we were to do so, the vacuum cleaner is the resource and the dirt are the entities, even though the dirt is stationary and the vacuum cleaner is moving. So the idea here is in our model, we might model the arrival rate of dirt as if dirt is arriving by some other process, as if it's just arriving spontaneously, when in reality, the motion of the vacuum cleaner is what's generating that arrival rate of dirt. So in the real world system, we might have the resource moving around, sucking things up, but in the modeled system that we build in Arena, the entities are the things that are actually arriving, moving, while the resource, like a cashier, is sitting still. All right, so any questions about that? Does that make sense? That your entities in your real system will often be the things moving around, but they don't always have to be. There are systems where the entities are actually sitting out there in the world waiting to be found, and the resource is moving around the world finding them. Okay. And I'll check questions online. Great. Okay, so last time we did this example where I had a car wash and basically showed that if you have a way to draw inter-arrival durations and service durations, so there's the inter-arrival duration between the entities, there's a service duration getting through the car wash, a service duration getting through the vacuum, and there might be times, for example, getting from car wash entrance to vacuum, from car wash entrance to car wash to vacuum, and maybe a time from vacuum to leaving. So could be a bunch of different times. So a time here, a time here, a time here, a time here, and a time over here. But as long as I have a specification for how long an entity waits in how long an entity takes in those activities, then I can start up a simulation and it will use all those activities to generate a timeline. And when I analyze that timeline, the delays will give me a relevant output. And that's all about this sort of scheduling, or this event scheduling worldview, where we start a simulation by scheduling the end of the simulation, a fictitious event, and then we schedule the first arrival. And we go on through this process of jumping to the next thing, saying, based on where we are in the current calendar, ask our process logic what we need to do when we process this type of an event, and then use the random distributions of, say, interarrivals and service times to schedule the next events. And that ends up allowing us to sort of pulling us up by our bootstraps, generate this whole schedule. And in doing so, we will eventually generate delays. And those delays were not known beforehand. These delays are from a mismatch in alignment from all of our activities. And those delays, how long these are, those are the important outputs we get out of running the simulation. And so we go on through that. So we're going to do that. That basically is a graphical version of your homework, the hand simulation. And we're going to do that concretely in the table here today, so that we're all on board on how to do that. All right, so any questions about that? Is this event scheduling worldview, does that make sense? Or does it not make sense? Just kind of going through the basics now. So no, it's a little slow, maybe not that exciting, but we're just laying down the fundamentals so we can get into more in-depth stuff about randomness and probability and all of that as we go forward. All right, great. All right, so this is your homework problem, basically. I give you up in the top right-hand corner a length of interarrival durations. So between customer 1 and 2, there's going to be 4 minutes or whatever. Between 2 and 3, there'll be 2 minutes, and so on. In practice, these things will not be integers. They'll be real numbers. But for simplicity, in the hand simulation, we make them integers. Likewise, with service durations, we're saying that when customer 3 finally reaches service, whenever that is, customer 3's, the number of groceries customer 3 has is going to cause it to have a 1-minute service duration, whereas customer 2 maybe has a lot more groceries. So when customer 2 finally reaches the cashier, it will take customer 2 a lot longer. It'll take 8 minutes. So these numbers would in theory be drawn from a random distribution normally when we do this, but in this case, we're providing the numbers ahead of time as if we drew them from a random distribution for you and just gave you that because you didn't have access to a random number generator. But in practice, these are typically drawn randomly as you're running the simulation. And that's all I'm kind of saying here. The first customer has no interarrival duration. That's on purpose because these durations represent the time between that customer and the customer before it. There's nobody before the first customer. That's why this thing is blank. I didn't want to put a 0 there because when you need to draw a new interarrival time, you need to know to draw that. So that's why it's just blank here. But really, these are 2 independent lists, and this list just has fewer numbers than this list because you didn't need one for that customer. All right, so any questions about the layout of this model? The only other thing I think I mentioned here is that this thing, well, I don't mention on this slide, but I also provide you an end time. So on the homework, I say the simulation ends at 30 minutes or 15 minutes or 45 minutes. So that's the other important piece of information provided. Otherwise, this is pretty much all you got. So any questions about the layout of that? Does that make sense? Okay. All right, so what do we do with that? Let me just make sure no questions online. Great, okay. So what do we do with all of that? We are going to manage our state variables and our cumulative statistics. So I already defined these state variables earlier and these cumulative statistics earlier. Just a reminder that the response time here is the entity's departure time minus the entity's arrival time. These services are not response times. The response times will always be at least the service time. So customer 2's response time might be 8, but it will not be less than 8 because if customer 2 has to wait, then it's going to take 8 minutes in the system just processing plus however long she waited. So if she waited another 2, then her response time is going to be 10. So we calculate response time at the instant an entity leaves the system by taking their current departure time, the current time, minus wherever they arrived. Now, in order to figure out when they arrived, we have to stamp them with their arrival time. So that's an attribute. So we are going to stamp each entity with an attribute, which just remembers for us, for our record keeping, when they entered the system. So customer 4 enters the system at a time that we don't know ahead of time, but our simulation will end up telling us. And the instant they enter the system, we stamp them with that attribute, which is their arrival time. So then when customer 4 finally exits the system, we'll be able to subtract the current time minus wherever that attribute is, that arrival time. So this is kind of a key thing. In order to calculate response times, you need attributes capturing arrival times. And this is why in most discrete event system simulation packages, they've got a hidden attribute that they already put on every entity that stamps them with their arrival time into the system. But in this class, we just to make it explicit so that everybody knows that's there, we sometimes force you to stamp them with that, because you can also do it yourself. But out in practice, you often have the arrival time for every entity because it's just built into the software package, because it's a really useful thing to know. Any questions about that? Does this make sense? This why we need the arrival time as an attribute. You don't think about arrival time when you go into the doctor's office, but my guess is they do keep track of arrival time for their own internal metrics. When you come in and sign in, sometimes they ask you to write, what time did you arrive? That isn't to shame you into arriving at your scheduled time. Well, it might in part be to shame you into arriving at the scheduled time because you have to admit that you're late. But it primarily, I think, allows them later to go into the records and say, oh, Mr. Pavlic, he arrived at 9:05. We completed his service at 10, and so he was here for 55 minutes. And so they needed me to write that down and to keep track of that so they can do their metrics later to see how long it's taking for them to turn over these patients. So we need that somewhere to be stored somewhere. All right, so how do we do that? So we're going to keep track of every entity as these records. And a record in this homework system is just going to be an ordered pair here. So it's just going to be a little tuple here where we've got C and then the customer ID, and that just number is going to increase for every customer, and then the arrival time. So customer 1 arrives at time 0. So that's the reason why we have this 0 there. And so I guess I should point maybe at the laser here. So customer 1, so this C just indicates that it's a customer type, and that 1 is just an arbitrary identifier, increase for every customer, and the 0 is the arrival time. Customer 1 always arrives at time 0. So what we do with those customers, we keep track of a state variable, which is the checkout line, which is an ordered list. So these customers we're going to queue up into this checkout line where the most recent customer is always the last list element. And the length of this list is always going to be the number of customers in the queue plus the number of customers in service. And so we call it a checkout line, but you can think of it as the customer getting service is the first one here. So this is customer 2 is in service. And the other 2 customers, 3 and 4, they're the ones that are actually in line. So they're the ones in a queue. So you can think of it as a service queue. So the service is the first one, the queue are the other 2. Okay, does that make sense? What I mean by, so we're just keeping track of how many people are either waiting for service or currently in service. This can be empty, in which case the cashier is sitting there waiting for someone to arrive. So LS plus LQ will always be the length of this list. I'll just pause there. Questions about that? Does that make sense? Okay. All right, now along with our customer records, we also have event records, and we have different types of events. So these records are structured differently based on the type of event. So we've got the first type of event we ever schedule is the end event, and that is, so there's going to be a future event list that kind of acts like the checkout line. We don't think of the future event list as a state variable because it's not technically available to our logic, even though the state variables are. And so the future event list is going to have these types of events in it. And so, and the first type is an end event. So it's just denoted with an E as the first part. And the time is the time at which the end event occurs. And so each one of these events is going to have a time associated with it. So you schedule the end event not at the end of the simulation, but at the beginning of the simulation, and you'll schedule it at this time in the future. Likewise, there's an arrival event, and that arrival event is going to have the time of the arrival event as the second part, or the second member of this event, or the second element of this record, and then the customer who arrived, that C1 there. So it's like A0 C1 would mean there's an arrival event at time 0 of customer 1. And then we've got a departure event. So when someone enters service, we immediately have to schedule a departure event. And we schedule a departure event by placing an event record that has this structure. D is the first one, just indicating its departure, the time of the departure, and then the customer who is departing happens there. So these things will be sloshed on to the future event list in whatever order they happen to occur in. And these can occur after the end event. We just won't ever get to processing them. So it is possible to schedule something after the simulation ends, but you just won't ever get to processing it. But we go ahead and schedule those anyway, just for good practice. All right, so questions about this? Maybe I'll go to the next slide and then ask. So all of those get placed onto a future event list, which will look like our checkout line, but its elements are these event records. So an example future event list would be this one. So notice that it's always in sorted order. So it always goes from left to right, the timing. So you might be scheduling something that is later than the first event on the future event list. Well, you have to make sure you place it in the future event list in the appropriate spot. And so if this departure event was already known, but the arrival event wasn't, then you would schedule the arrival event where it properly belongs, which is in between this 11 and this 60, and that comes out that. So this represents that the next thing that's scheduled to happen is a departure of customer 3 at time 11. And then after that, we know that there will be an arrival at time 15 of customer 5, and then there will eventually be the end at time 60. Other things might happen. When this customer departs, there will be more things that get scheduled. When this customer departs, it might be idle, but eventually there's going to be an arrival, and that arrival is probably going to generate a departure event. So this is just telling you things that we know are going to happen in the future, but it doesn't tell me all of the things that are going to happen in the future. We don't know that until we run the entire simulation. So as we run the simulation, we get more information about things that happen in the future. All right, any questions about that, about the future event list? Also looking online. All right, there was, there's a question that was related to something on a previous slide, which I'll get to in a second. Are there any questions about this in particular? Is this pretty clear? Yeah. So there's a question that there is an event, a departure at time 11. So the question is, could you also have an arrival at the same exact instant? And yes, you could. There's nothing that prevents that from happening, but when that happens, then you effectively do the logic. When you get to time 11, you'll do the departure logic and the arrival logic. But it usually ends up being safe to do the departure logic and then just pretend like you didn't notice that it was simultaneous. And then the next time you'll go back, you'll go, oh, I'm still at time 11. So I think conventionally you do them all at the same time. So you don't have a double clock entry where you'll get clock equals 11 departure and then the next row clock equals 11 arrival. But in theory, you could have two lines that are separated with no time in between. But yes, absolutely, these things can happen. Now, because these timings will almost never be integers, there's a probability 0 chance that you'll get simultaneous events. So because these are all Poisson processes, usually these arrival events You know that with the Poisson process, you learned in 470 that simultaneous arrivals happen with probability 0. That doesn't mean they can't happen, but that ends up happens. It's super, super rare. So you almost never have to worry about that in real life. But you can in homework assignments, because I might not be clever enough to prevent that from happening when I come up with these numbers. Any other questions about this? All right, so there was a question online. In the case of modeling a vacuum in which the entity is fixed, could the same logic be applied in a hospital in which patients are fixed and different doctors come in and out of the office as opposed to patients moving? So that's an excellent example. And yes, I think that is one way you can model that, is that you can think of managing a doctor's schedule protocol for doing rounds. You can think of the doctors being the resource because patients wait for the doctors. But the interesting thing in a hospital is patients in a hospital bed, they don't come to the doctor and wait for the doctor. They have to wait for the doctor to come to them. So that is a perfect example of another case where the entities might be fixed, stuck in a bed, and the doctors might be mobile resources. And if we're just focusing on the doctor, then we might model the patients as arriving at the doctor, even though on the hospital floor, the doctor's arriving to the patients. So that's a great question. All right, any other questions? All right, so how do we execute this? So we got this stuff up here. We know that the end event is whatever I said, 60 or something like that. So how do we go through this? And so if I happen to hit an arrival event, then I first look at the checkout line. Or I could look at these two new variables, LS and LQ. So if LS and LQ sum to 0, or if the checkout line is empty, then I take this arrival event, which tells me which customer is there. And then I say for that customer, I am going to put the customer into service. And so the way I do that is by scheduling a departure event with that customer at whatever the current time is, plus the service time associated with that customer. So if customer 2 is here, they have a service time of 8 associated with them. So if I happen to be at time 6, then I would have time 6 plus the 8. Well, 6 plus 8, I hate to do math in public, but I think it's 14. So then I'd have D14 C2, which would be putting that upcoming departure event into the event calendar. And then because I've now put someone into service, then I have to increase the number of customers in service by 1. So it'll go from 0 to 1. So you could just say I'm going to set it equal to 1, but I just do this in the general form because technically your server could have more capacity than 1. And so this is technically what's going on. But in this case, it only has a capacity of 1. So it's either going to be 0 or 1. Otherwise, if on arrival event, the checkout line is not empty, the customer has to wait. And so how do we model the customer waiting? We're going to put the customer in the queue. And so because the checkout line isn't empty, they will naturally be the second or third or fourth entry in the queue. And we are then going to increase the count of customers waiting in the queue. So the number of waiting at a particular instant. What we always do is then, for either of these cases, is put our new customer in the checkout line. And because we have finished processing an arrival event, we have to schedule the next arrival at this inter-arrival time in the future. And so we then schedule the next arrival. If we forget to do this, then our arrivals will just stop. There's no way to rescue us from this. The only way to get to next arrival is to schedule a new arrival after the previous arrival has left. All right, so any questions about this process? We're going to do this with a numerical example where we apply this and build the table up. But this is the logic we're going to use every time we hit an arrival event. So this logic makes sense. Okay. I'll double check online, give people more time to think. Okay. All right, so then what do we do on a departure event? So if we happen to grab a departure event off the front of the future event list, then the first thing we do is increase. So I'm only using ND and S. In your homework, you also have that F one as well. And I think in the example that I do on the video and the homework, I might also handle the S. But for simplicity here, I'm only going to do ND and S. So ND is the number of departures. On a departure event, we have had a departure. So we increase our count of departures. On then we also need to increase the cumulative service time or cumulative response time. And so we're going to take whatever the previous cumulative response time is and add to it the response time from this customer, which is the current time minus their arrival time, which we have in their customer record. We know when they arrived. So that's the total time they were in the system, and we're adding that to the cumulative response time. Then, because they've left, we take them out of the checkout line. So we remove them from the checkout line, and that means we can decrease the number of individuals currently being serviced. Now, if the checkout line still has others left over after we've done that, then now we have to schedule the service for the one who's been sitting there waiting, who now can enter the service. And so even though we've just decreased the number in service, we then re-increase it because, and you could of course skip this step if you can see what's going on here, but this is the general thing that a computer might do. So we're going to now say, well, now there was one fewer in service. Now there's one more in service because we took one out of the checkout line. And now there's one fewer waiting. So we are taking that one fewer out there. And because someone has now entered service, they're going to eventually depart service. And so we now know that we need to schedule their departure event. So we're going to schedule that departure event. We're going to add a departure event to the future event list, which will be the current time plus whatever service time is associated with that customer. And then that customer is the next customer in the checkout line, and the service time is the next service time from the list. And so, so the way I've organized this, then it goes straight down the list. But you could, it's like customer 4 will always be this one, customer 5 will always be this one, but you're really technically just drawing from the next number in the list, as if you're drawing a number from a random number generator. All right, any questions about the departure events here and why these variables move the way they do? Whenever you process a departure, this is what you do. On every single departure, you do all of these steps. That seemed natural. Just checking online. Okay. Okay, and then the last event, the simplest event, is an end event. So whenever we get the end event, we terminate the simulation. So there are certain logic that we might apply here. So on your homework, and this matches what the book does, I'm okay that you do not have to create a separate row for the end event. When the end event is the next event, when you finish processing the row that produces a future event list where the end event is the next event, you can stop. Technically, you could, I guess, go forward and process the end of it and create a separate row that doesn't change any of the state variables, but removes the end event from the future event list and moves the clock to the end. That's fine if you want to do that. I'm not going to mark off for that. They're also fine with you just doing like what the book did and just stopping at the row before that happens. The row that where the end event is the first thing on the future event list. So, so what does that look like? So now we're simulation time for 15 time units. This is again very set up just like your homework problem. So I've got a table. This is a table just like in your homework problem, except you've got an F column as well. So what am I going to do? Well, I look and I say, the thing I know is that this simulation is going to end at time 15. So the first thing I do is put time 15 in the future event list. Now I'm going to animate this timeline down here. You don't have to do this in your homework. The timeline, don't worry about that. That's just here to hopefully help as a visual aid in what we're doing in this list here. You don't have to bother with this. You just have to populate the table. So end event, I put in the future event list first. Now do it in pencil because you might have to move things around as you go here. So that's why it also helps by maybe doing this digitally. So I know the next thing I have to do is effectively schedule an arrival event at time 0. Now, you don't have to worry about formally scheduling that arrival event, but we imagine it was scheduled at time 0. So we are going to imagine that we're processing that arrival event That's where we kind of start the simulation, when you're processing that first arrival event. So customer one arrives at time 0. Try to use the mouse laser pointer as much as I can here. And so then what happens when you process an arrival? Well, let's think about it. The customer arrives, the LQ plus LS is equal to 0. The checkout line is empty. That customer can go straight into service. Since that customer can go straight into service, I can look up at their service duration and schedule when they'll get out of service. And so that's what we're going to do here, is that we know that if customer 1 arrives at 0, then 1, that's their service time unit later, they will depart. So we're going to schedule that departure event in the future event list. That's what we did here. We scheduled that departure event. That 1 is effectively 0, the current time, plus the 1, the service duration up here. All right, now we have to manage all these state variables. Well, we now have 1 customer being serviced at this time. So we increase that from 0 to 1. We have got 1, that customer 1 is in the checkout line. We're adding them to the checkout line. So this little down here, this is me just following the steps that I went over in the last 3 slides. And then, so imagine this stays 0, that's 1. We added them to the checkout line. Now, the other thing that we have to do is, because we just processed an arrival, we have to schedule the next arrival. So I look up at my table here, and when I look up at my table up here, then I see that the next inter-arrival time, in other words, the time between customer 1 and 2 is 4. So I have to add 4 to the current time and schedule that arrival in the future event list. And then I go forward and I just fill in the rest of the state variables that didn't change. And so there's still nobody in the queue waiting. Nobody has departed, which means our cumulative service time is 0 because nobody has actually finished service. All right, so any questions about that first row? And I'll go a little more quickly through the other rows. That makes sense how we populate it. Yeah. In the 0, so the question is, in the checkout line column, what does this 0 represent? That's their arrival time. Customer 1 arrived at, so it's keeping a record of when they arrived in the past. Okay, great question. Any other questions? All right, so what do we do? Now we need to populate the second row. We jump to the first event in the future event list from this row. So the first event is a departure at time 1. That tells me that I'm going to jump to time 1. So this next row is going to be at time 1 because that's the first event in the future event list from the previous one. So I go to this second row and it's a departure event. So again, that's the first entry in the future event list, is departure event. So because it's a departure, my first step is to increment the number of departures. So I'm going to take whatever it was in this row and add 1 to it. And the service time is whatever the cumulative the cumulative response time was in the previous row. And I'm going to add the response time for this customer. Well, I'm currently at time 1. The customer arrived at time 0. So they spent a total of 1 minute in the system. So that cumulative service or response time goes from 0 to 1. I'm going to remove customer 1 from the checkout line here. So it'll be an empty checkout line. And I'm going to reduce the number of customers currently in service because this is a departure. So there's 1 less in service. And I'm now moving the clock forward to that time. So all of that accumulates into this second row right here, where I've moved ahead to time 1. There's now nobody in the queue. There's nobody in service. The checkout line is empty because nobody's in the service and nobody's in the queue. The future event list is a copy of the previous future event list, but I've removed the departure event. I don't schedule any new things into the future event list because there's nobody in the checkout line, and this is a departure. So the arrival's already there and ready, but the cumulative statistics have gone up. The cumulative response time went up by the response time, and the number of departures went up. Any questions about that row? Does that make sense? Okay. So let's jump ahead to something more exciting, another arrival. So now customer 2 arrives. I'm going to jump to, again, the first event in the future event list is an arrival at time 4 of customer 2. So I'm going to jump all the way to time 4. And when I jump to a new arrival, because that arrival arrives to an idle server, I can immediately schedule the service departure because they'll go directly into the cashier, directly into the server. So I look at their service time, which is up here, their service time up here, and that service time says 8 minutes from now, they'll get out of service. And so just statistically speaking, what we're going to predict, it's going to take them 8 minutes to get out of service. And so that's why I'm going to schedule a departure for 12. That 12 is the current time 4 plus the 8 of their service. I then now, because they've moved into the server, I increase the service time state variable by 1. I'm going to put them into the checkout line because the person being serviced is the head of the checkout line. And then because I've processed an arrival, I'm going to schedule the next arrival, which up here happens 2 minutes after this arrival. So that's what I've scheduled there. And I move the clock forward, and that's how I get that third row. So that's that whole row there. We can see them in the checkout line. We can see the next thing to process is an arrival. Then there's their departure, and then there's their exit. Any questions on this here? Before we move on to the next row, where things get really exciting when someone arrives while the server is busy. Yeah. Yeah, there's a great question. So the question here for those online who can hear is there a reason for the ordering of departures and arrivals in the future event list? Does anybody have an answer for that or a guess for that? Yeah. Great. So the answer there was C3 will arrive before C2 leaves. That's right. So the future event list is always sorted by the timing of the records. So it's not always the departures are before arrivals. It's that this arrival is before this departure because this is a so-called priority queue. Questions about that? Does that make sense? Questions online? Okay. All right, so let's see what happens in the next, this more exotic case, where I jump ahead to time 6. At time 6, customer 3 is going to arrive, but they arrive to a busy cashier. So what's going to happen? Well, they're going to have to wait. So we add them not to the server, we add them to the queue. And so the length of queue is going to go up by 1. And then we have to put them in the checkout line behind the customer that's currently in service. And so there'll be 1 more in the checkout line. We then, at this point, because we have processed an arrival, we can schedule the next arrival. So we can look up in our table and we can say that the next inter-arrival time that we haven't used is 1. So we're going to add 1 to the current clock, and that will be the next arrival. And we'll move a clock ahead. So we didn't do a whole lot there. But that this will end up helping us bookkeep how long this customer is going to end up waiting there. So in this row here, we've jumped ahead to 6. We increased the queue. There's now 2 in the checkout line, and that customer just has to sit there and wait. Their departure is not scheduled. You're going to be tempted when you do your homework assignment to think ahead and say, you know what? I know ahead of time that customer 3, well, I know that customer 2's service is going to end at 12. And I know customer 3 has got a 1 service duration. So I know the customer 3 is going to depart at 13. I just know that in my head. So I'm going to go ahead and schedule that additional departure. You just simulate it in your head. Don't do, we want the whole simulation to happen on paper. So don't try to simulate ahead in your head. Follow the process here and you will never have more than one departure in the list. So even though you internally know that next departure could happen at 13, we want to go through this process. And for a simple single channel queue like this, it's safe to do it in your head. But as we get to more complicated systems, because things can be input or added to the middle of the future event list in ways that you might not anticipate, you might think the next departure is going to happen at a particular time. But imagine we were simulating service failures. We will learn about failures in one of your upcoming labs. And there could be a failure of the server that prevents it from doing its work. And then you would have inappropriately scheduled the departure for time 13 when that failure takes the resource down and you have to wait for the resource to come back up. So there could be other intervening processes that prevent you from being able to jump 2 steps ahead. Question or is it a stretch? And then like I guess card 3 and then card 4 would come in before the departure time. So that's a great question. So you say, well, shouldn't I be able to schedule all my arrivals all up front? And for a simple system like this, you probably could just schedule all the arrivals up there, but it's a lot of work because these like are only going up to 15. And so you might end up like taking all this time to calculate the arrivals of the 100th person. And in the end, you only have to simulate the 15. More practically, you're not going to get a list of these numbers in a real simulation. You're going to get an average. On average, people arrive, with 5 minutes between them. So you're not going to be able to look into the future. You just draw an arrival when you need an arrival, as opposed to drawing 100 arrivals ahead of time. Any other questions? All right. So let's see if we can get some more customers out of here. So we know the next arrival happens at time 7. So we're going to jump to time 7. It's an arrival event. So that server is busy. So it gets added to the queue just like before. And it gets added to the checkout line just like before. And because we processed an arrival, we have to schedule the next arrival. So we schedule C5 based on that inter-arrival time. And so in this row, our future event list, we just pop out that arrival and basically replace it with a new arrival. We add one to the checkout line, and that's it. Bob's your uncle. So then, we just can move ahead. So we can now process this departure we've all been waiting on. So we get to this departure. The first thing we do, increase our departure counter. We then increase our response time counter. This customer who's departing, C2, well, if I look, C2 arrived at 4. They're getting out at 12, because that's when this time happens here. So they spent 8 minutes in there. So I'm going to take whatever the previous service time was, 1, the cumulative response time, add 8 to it, and I get the 9. And then I remove that customer from the checkout line. By doing that, that is going to allow and then it's going to remove them from the server. So I do this little step, but this little step is going to get undone quickly because we see that the next customer 3, is sitting there waiting. So we can immediately put them into service. So we increase that service time back up, just undoing our previous decrease. We decrease the number that are in the queue, and then we schedule the departure of customer 3 by looking at their service duration, which is 1 minute ahead of the current time. So we schedule them for 13 to depart. And that finally, finishes that row where we did a lot there. So we were getting rid of some and we were adding some, and we were doing a lot of scheduling or whatever, and we get to that row there. And I can keep going on that. And so I'll just, the next one will be a departure. So I just did the same thing over and over again. So there's my completed table. Are there questions about this table, the way it looks, the process we went through here? And this is where I can end in the homework, where at time 13, I see that the next thing I would do would be jumping to the end. So in theory, you could have a time 15, which would look just like 13, but it wouldn't have the end event in the future event list. But we don't actually have to do that. It's fine to stop here. Won't take off points if you do it the other way. You can do it both ways, but the book stops here, and I think it's fine to stop here. Yeah. Great question. So, so the question was, in a checkout line column, how do you know when to take the customer out of the checkout line? Does anyone have an answer to that? On what type of event leads to someone coming out of the checkout line? How many people say arrival? How many people say departure? A lot of departures. Sorry, online, I could have done that poll there too. But in class, most people said departure. So that's right. So on a departure event, one of the key things you do on a departure event is you always remove somebody from the checkout line. On the departure event, you always remove from the checkout line. You always increment the number of departures. You may have to change this cumulative service time, and you'll have to adjust the LQ and LS appropriately. So on a departure event, you're going to remove one from the LS, but you might end up re-adding it if somebody else is in the checkout. Does that make sense? Okay. Any other questions about this table? Yeah.
For what purposes would we just want to even schedule events after the end event, like the arrival?
No, I'm happy for you scheduling events after the end event. You know, you could say, well, I could optimize that and not schedule them after the end event. But for now, I actually want you to schedule them after the end event to show that you're going through the process logic. Because again, we don't want the future event list. We kind of, again, it's a priority queue, which means we want to be able to grab the, imagine that you can't see anything in the future event list except for the first event. So that's kind of the way the computer views it, is that it can schedule things and it's trusting that another process opaque to it is going to put them in the right order. And then it'll grab the first thing off the list. So you, as the human, can see the whole future event list, but really the computer, the simulator, which now is also you, can only see the first element. And that first element isn't always the end. So you may not know that you're scheduling beyond the end of the set. Any other questions about this table? Questions online? Oh, there's a question online. For the cumulative statistics column, how did it end with 16? It ended with 16 because the last event was a departure event for customer 3, and customer 3 departed at 13, arrived at 6. So again, I hate to do math in public, but if you do 13 minus 6, I think that's 7. And so 9 plus 7 gives you that 16. So it jumps from 9 to 16 here because customer 3 departs and it is in the system for 7 whole seconds. Does that help online? All right, so what I'm going to do here is I'm going to jump ahead to the attendance exercise. Happy to take a couple of questions here, but I don't want to keep anybody longer. So just this question today. I'll put the URL in the chat. Looks like online was helped by that. Great. So question for today is, how many arrivals will ever be in the future event list for these single channel queues, single channel, single server queues? How many arrivals will ever be in the future event list? What are the possible numbers of arrivals that you'll see in the future event list? And I can type that in the chat as well. And that's all I've got for you today. So if you don't have any other questions, you can feel free to take off. Otherwise, I'm happy to hang around for a couple of minutes if anybody does have any questions. And have a good weekend. If anything comes up, feel free to send me an email, post on discussions, post on Slack, etc. All right. Anyone online have any questions? If not, I will be closing the Zoom room momentarily.
Let me